Welcome to this webinar. My name is Mohsen Nazami. I'm a PhD student at ETH Zurich, based at their Future Cities Laboratory in Singapore. Today, on the World International Bicycle Day, I will talk about my research, which was about the virtual reality method in bicycling research. Please feel free to write down your questions in the box that is provided in the right pane. I will get back to your questions at the end of this session in a question and answer. The duration of this talk will be about 40 to 45 minutes. Okay. I start my presentation by giving you an overview of the previous research in the literature about the bicycling. This table is adopted from the Lausanne et al. In 2013. They had gathered these studies up to the year 2008, if I'm not wrong, and I have updated this table to 2019. This table shows how the focus of the research was on the link-based, for instance, or at the intersection level, or at the citywide level. The people who have been surveyed and the purpose of the study, which it was whether perception of safety, comfort, or something else, and the survey method, which is the key input for us here. If you want to categorize the whole studies, we understand that there are three different groups of research aims. The first one is bicycling behavior. This can be interpreted in two things. The first one can be simply the questions that have been asked regarding the bicycle frequency, how often people cycle to different locations. Usually for these type of surveys, paper-based questionnaires or web-based questionnaires were used. Or the bicycling behavior can also be interpreted as as understanding the choice of the speed, the braking behavior of the bicyclists, and so on, using bicycle simulators or equipped bicycles in the field. The second category would be infrastructure preferences. It means, for instance, the choice modeling surveys, where they wanted to find out usually the trade-off between the bicycling environments and also the duration of the bicycling, for instance, how long people would consider cycling in different environments. The third category is bicycling perceptions, mainly, for instance, asking safety and comfort of the participants when cycling in different environments on a Likert scale questionnaire. This is actually the focus of my research. Again, if you want to categorize all these studies, we can also categorize them based on the methods and materials that they have used. They were either surveys. They used telephone surveys to ask people about, for instance, the bicycling frequency, as I mentioned, or their perception of their environment regarding how cycle-friendly their neighborhood is, so on. There have been intercept surveys asking people in the field, the bicyclists, okay, how do you rate this stretch of the road that you just cycled on? Or the other type of surveys in which they use text, images, illustrations, or video clips to convey the message, to actually describe the intended design to the participants and ask them about their preferences and perceptions regarding any of them. There have been also mental maps asking people to show their daily commute to their work or to their school on a map and show, for instance, which part of the road has been more stressful or unsafe for them. This is also another type of surveys. The second group is field studies. In the field studies, they either use, for instance, equipped bicycles to do the measurement of the speed, the braking activity, and some other stuff. They usually have these video cameras on the handlebar to detect the stressful moments that the participants encounter. And sometimes participants were attached to different type of sensors, physiological sensors, to gain more insight into their behavior while they were cycling. The third category is simulators. They are obviously based in the laboratories, and they use mainly two different types of presentation methods, which is video simulation, in which the participant sees a video. He or she cannot interact with the agents in the simulation. However, in the interactive simulation mode, the participants can interact with any other agent, and the other agent, meaning the cars or the pedestrians, would react to their movements as they change their position in the scene. So what was studied in my research was video simulation. It was not an interactive simulation. Looking into Singapore, this is a photo taken in 1966, shows how workers used to commute to the port in Singapore by bicycle. However, things have been changed since that time. Bicycling experience and bicycle motor is very low at the moment in Singapore. It's about 1% only. Therefore, the classic survey methods might not lead to adequate and reliable results anymore. The aims of my research was to study the capabilities and limitations of virtual reality for bicycle research. We wanted to see if we could push the boundaries of classic survey methods further. And we wanted to compare the virtual reality experiment results with classic video-based surveys that is frequently used in the bicycling research. But why virtual reality? It gives an enhanced sense of place to the participants with an eye-level perspective. It's very easy to create variations in the designs. You can easily change the traffic speed, volume, proximity of traffic to the participants, and the number of pedestrians, and so on. The scenarios are replicable to all participants, meaning that each individual will experience exactly the same design that the other participant has experienced. So we have a full control over this environment, and we are actually surveying the participants in a very safe environment, which is laboratory. Today, we are going to explain the procedure of creating 360-degree videos using PTV Vissim, and also summarize the findings of my experiment. The first step is to create a street design. We use City Engine as a software that is used for procedural modeling. It means that we use some code to generate the 3D model of a city that you see here, composed of streets, buildings, and so on. Based on this code, which is called the rule, you are able to quickly generate some 3D model of a city. We use the complete street rule developed by Esri research team, and we further developed it to match Singapore condition and to our modeling needs. The code is also available on GitHub, and the link can be seen here. The second component was the traffic microsimulation. Here we had some challenges. You might be all familiar with the PTV Vissim and its capabilities. However, for this specific purpose, we wanted to use Vissim for other purposes. We wanted to obtain the trajectory of the pedestrians and the motorized vehicles in a very fine level, and to later show it to the participants at the virtual reality. So we needed a very fine movement of the people and the motorized vehicle. What we needed to get was the geometry that was taken from the previous step, from the street design. We wanted to have unpredictable modeling of the pedestrians and pedestrians when they are walking on the sidewalk. So later I will show you how they are moving in an unpredictable way on the sidewalk by just creating some imaginary obstacles on the sidewalk. Otherwise, they just walk on a straight line on their shortest path to reach their destinations. We wanted to have the interaction of pedestrians and bicyclists and vehicles as smooth as possible. Here we had the issue that pedestrians follow the social force model, and the motorized vehicle follow the car following model, and these two different models are not communicating well in Vissim. So there are some limitations in that regard, but I know that the PTV Vissim team is working on that to enhance it. Even though there are some options to model the bicyclists as pedestrians, and we tested that, but we didn't have such a fine movement of the bicyclists as pedestrians, so eventually we modeled them as the motorized vehicles as well. So the areas that we wanted to model in some scenarios was shared space. We wanted to have the interaction between pedestrians and bicyclists. We had some limitation in that regard. And The interface between Vissim and Unity needed to be created for having the final output. The third component of this study was the Unity, which is a game engine for better representation of the model to the participants. From the city engine, we got the 3D models. From PTV Vissim, we obtained the trajectory of the vehicles, bicyclists, and pedestrians, and the timing of the traffic signals. We obtained some 3D models for, again, better representation of the objects in virtual environment, and we all imported them into Unity. What we needed to do in Unity was to have a finer modeling of the movement of the agents in a fraction of a second, just to have a smooth movement. For instance, we also needed to adjust for the vehicle wheel rotation. We needed to adjust for the brake lights of the vehicles when they are reducing their speed. And we needed to animate the bicyclist pedal when they are pedaling, and so on and so forth. And the traffic lights, for instance, these are the small details that you needed to adjust in the Unity. And then when you model everything, then you can have different types of output. You can have high visual quality renderings for presentations and surveys, just to use an image, for instance. You can use videos of moving traffic in 3D environment. You can have 360 videos for immersive virtual reality experience, and also interactive virtual reality applications with real-time traffic reactions, which will be the future work. When you have created such an environment, then you need obviously some display mode to be shown to the participants. There are some different types, like the classic monitors that don't have any immersion. We also have caves. It's essentially a room. You have the video on different on the sides, and also at the ceiling, and also at the floor. So it's kind of immersive. It has some benefits. For instance, people don't get motion sick, but it's not obviously as immersive as the head-mounted displays that are frequently available now on the market. What we used for this study was the HTC headset, which was used for tracking head and hand movements. Finally, how the movement was captured. It can be no movement obviously in the scene. You just stand, you see around, nothing happens. It can be a fly-through, meaning that it can be a video out of the 360 environment shown to you, or you can have control over your movement in virtual reality via keyboard or joystick. But in order to just enhance this feeling of moving in virtual environments, you can use treadmills for walking purposes, walking treadmills, as you can see in the picture, or bicycle simulators. This is the photo of the bicycle simulator that was designed in the laboratory to collect the information of the participant and then show their position in their 360 environment for the experiment. This is how the bicycle simulator works. We had different Bluetooth sensors for the acceleration and speed, pedaling, braking, and steering. The sensors collected the information on these movements and captured these in the virtual environment. And the head movement was also collected by the head-mounted display. We created an experiment called Bike to the Future. As you can see in the photo, there are different inputs. Participants were seated on a bicycle simulator. Participants could brake and pedal, but the steering was disabled because during the pilot tests, we realized that steering in virtual environments is very hard for participants. And also, more importantly, it makes them feel motion sick. So we didn't obviously want to create such an uncomfortable feeling for the participants. So we completely deactivated the steering wheel sensor. And also, for instance, to ease the transition between VR and reality, we also used those sensors on the pedal to capture the movement of the participants in reality and in VR. If they were synchronized, so they could see the hands, for instance, on their steering wheel. These things also helped the participants. As you can see, there are three data sources available in this research. The first one is the questionnaire that was running in parallel all the time to the experiment. The movement measurement was collected by the bicycle simulator, and the physiological sensor was collected to the participants during the whole experiment to measure their stress level. The experiment design is shown in this photo. It was about 45 minutes, and the participants were compensated for 15 Singaporean dollars for their 45 minutes of their participation. What we are going to discuss today is from minute 25 to 40, in which participants were cycling through 6 different environments. The first one was actually an orientation scene, just to familiarize themselves with the bicycle simulator and how to cycle in virtual environments, and subsequently 5 different scenes to cycle through and answer to the questionnaire. Here you can see all the 5 designs that we created. They pretty much look like Singapore. That's what we wanted to have. The first one is a sidewalk. They were just cycling next to the pedestrians. No specific bicycle facilities available here. The second one is the painted bicycle path on the sidewalk. All the dimensions are the same. The number of the pedestrians are the same. Everything is the same except for the painted bicycle path on the sidewalk. We have painted bicycle path on the road, roadside cycling, and segregated bicycle path. The whole stretch of the road was about 380 meters, and there was an intersection in the middle just to observe the behavior of the participants when they arrive at an intersection. We can actually have a quick survey here, just for yourself. By looking at these 2 images, painted bicycle path on the sidewalk and painted bicycle path on the road, which one do you prefer to cycle? So you just have a standstill image. Based on these 2, you can have one choice. Later we will see how your choice might or might not change by seeing a video out of these. And it might also change when you actually bicycle in these environments with the bicycle simulator. Here I show you the video of these 5 environments. Obviously all these videos have audio, but unfortunately I cannot present it to you on this platform. We have the noise of the vehicles and the white noise at the background. You can see the movement of the pedestrians on the sidewalk. Sometimes they are just moving towards your bicycling path. Those are the unpredictable behavior in the walking behavior of the pedestrians that we wanted to have, and they are the outcome of having the imaginary obstacles in the Vissim model. This is the existing situation in Singapore where there is no specific infrastructure available. The participants are cycling on the roadside. So all the dimensions are exactly taken from the reality, what we have in reality in Singapore, the lane width, so on. A painted bicycle path on the road. And a segregated bicycle path. And here is the finish line after 380 meters of cycling. Okay. Participants were mainly recruited from the National University of Singapore and Land Transport Authority of Singapore. We surveyed about 150 participants. We had the gender had a good balance, but age distribution was obviously not representative of Singaporean population. And they were mainly 18 to 34, and they mainly had a university degree. We asked participants about the main barriers to cycling in Singapore, and the first 3 reasons were identified as safety concerns, comfort concerns, and unavailability of appropriate bicycle facilities. We asked 5 different questions regarding the perceived level of safety. We asked specifically about safety due to proximity to pedestrians, safety due to proximity to cars, safety due to volume of the cars, safety due to the number of pedestrians, and if the participants were worried about occasional pedestrians or cars coming to their path when they were cycling. So these 5 questions were repeated after any of those 5 scenes that you saw, and we collected the data on a 7 Likert scale question. It can be seen how the segregated bicycle path was safer than roadside and painted road due to proximity to cars and due to traffic volume. However, this traffic volume was exactly the same for all the 3 environments that I mentioned. So it can be seen how just having a nicer bicycle facility can influence your perception of the number of the cars or the volume of the cars and enhance it just by having a better facility. We also asked about the safety due to proximity to pedestrians and due to number of pedestrians for the 2 environments of painted bicycle path on the sidewalk and sidewalk. We realized that PLOS was higher when they were cycling on a painted sidewalk compared to bicycling on the sidewalk. Again, the number of the pedestrians were exactly the same for both scenarios, and the difference in the answers given by the participants was due to having a nicer bicycle facility. And it shows how a bicycle facility can enhance the perception of the people with regards to safety. The other question that we asked was the willingness to bicycle. Participants were asked whether they would be willing to bicycle on these facilities for less than 10 minutes, for more than 10 minutes, accompanying a child, and at night. Obviously, not all these scenarios were replicated in virtual reality. Participants still had to imagine when they are cycling for less than 10 minutes, more than 10 minutes with a child and at night, because they were only cycling for on average 80 seconds in each of the environments. It took them 80 seconds. So again, there was some imagination needed here. The segregated bicycling facility was preferred. Bicycling on the sidewalk with a painted bicycle path was preferred over a painted bicycle path on the road. So people prefer to be next to the pedestrians and farther from the motorized traffic. And introducing a painted bicycle lane on the sidewalk had a huge impact on the willingness to bicycle, as you can see in the images. Going to the second data source, the bicycle simulator, we can see the speed distance graph for all the 6 environments, including the orientation scene. Here you can see the average speed distance. There are 3 different environments with specific bicycle facility, and the other 3 don't have any specific facilities. The highest average speed belongs to the segregated bicycle path and painted bicycle path on the road. They are the solid lines on the top. The local rises and falls that you see on the graph shows the stop and goes due to encountering adjacent pedestrians or vehicles, which affects obviously the bicycling comfort level. They are noticeable especially on the first 150 meters of the design before the intersection, when everything is new to the participants. They are completely unaware of what is going to happen in each scene, and they are perfectly responding to each of the events that are happening in the design. And here are the fluctuations. They are mostly observed in the sidewalk, which is this light blue line, and also on the green line, which is the roadside. And here you can see how the average speed also declines right before the intersection. They brake to check for the cars and then cross the intersection. Obviously, these graphs can be also derived based on gender. Overall, we can see men rode faster than women, and this difference is more noticeable when there was a bicycle infrastructure available, particularly when you see the segregated bicycle path and painted bicycle path on the road. This difference between the 2 graphs of male and female is more noticeable. We also analyzed the head movement and braking activity of the participants. In order to analyze these results, this data, we had to segmentize the whole stretch of the road into smaller sections. We came up with six different segments: start, segment 1, before intersection, intersection, segment 2, and end. We built some mixed models to incorporate the between subject variability in the model. And the results for the head movement showed how participants significantly turned their head right before the intersection. They turned their head more to the right and to a lesser degree to the left because the traffic drives on the left side of the road in Singapore. So they were checking if there are any motorized vehicles turning into this small intersection here on the right side, and then they crossed the intersection. We also analyzed the braking activity. Participants brake more at the intersection and prior to the intersection, as was expected. It's also replicated here. And if we analyze the braking activity for the whole environments, for the whole stretch of the road, we realized how overall braking was significantly used more often when bicyclists were cycling on the sidewalk. And the results are corresponded also to the bicycling behavior expected in the reality. You encounter much more events when you're cycling on the sidewalk because of the unpredictable behavior of the pedestrians next to you. We go to the next data source, which is the physiological sensor. We use an electrodermal activity sensor, which collects your sweat level at the skin. It's connected to your hand. And the more you sweat due to encountering different events, the higher would be the stress level of the participant. Here you can see an image of this sensor. This is the interface of the experiment. The participant starts cycling on the sidewalk next to the pedestrians. There can be different stimuli when you are cycling on the sidewalk. For instance, the unpredictable behavior of the pedestrians next to you. And here you see on the box, we are looking into the number of rises of this graph and also the magnitude of them. So the arousals are shown on the white box on the left. And later we analyze this signal via signal processing techniques. Here you see the sudden movement of the participant to the bicyclist, sudden movement of the pedestrian to the bicyclist, and then subsequently there is a rise in the stress level, as you can see in the white box. Now we are on the fast forward. There are some other encounters and some subsequently other arousals happening. Now the participant arrives at the intersection. Intersections are generally very stressful to the participants. Again, the participant checks and crosses, and then you can see how there is suddenly a much higher jump in the signal observed as compared to the previous arousals that were due to encountering pedestrians. So later we also analyzed this magnitude. I think this is for the same participant while he or she was cycling on the roadside. There are different sources of stress when you are cycling in this environment. If you just look at the white box, you will see that there is a arousal happening already while there is nothing in the screen. However, after a few seconds, you see the bus passing by. And this bus was actually the source of the stress because the participant heard the noise of the bus getting closer to him or her. And that was the source of the stress. So all of these are captured via this sensor. Now, when we analyze this data to identify the location of the skin conductance responses for the 6 different environments, I hope it's readable for you. The first one is test scores, and the 5 ones afterwards are the 5 scenes. This figure shows only, out of 150, only 89 participants had good data for this physiological sensor that could be used for the analysis. They were standardized to T-scores to again account for the variability within subjects. The figure shows the top 1 percentile of T-scores for better clarity. So this is the highest arousals in the whole data set. These arousals can be due to different stimulus, the presence of the pedestrians, vehicles, and so on next to the bicyclists in virtual reality, the stress of crossing an intersection, the excitement of passing the finish line, and other non-specific arousals due to unknown stimuli. Even if you visually check here, you see for this column how the density of these arousals are more as compared to the other segments. You can also observe this density for the whole stretch of the road, for the roadside, for instance, and for the sidewalk, which visually can be seen more or less how participants had more arousals when they were cycling on the sidewalk and roadside. But this analysis has been done for the segments just to have a more robust analysis. And here you see for each of these segments the results. The mean arousal amplitude of 89 participants for each segment is presented in this figure. Segment 1 best explains the net effect of the bicycling environment on the stress level of the bicyclists, because there is a phenomenon happening in these experiments called habituation. After a few seconds, participants just realize that, okay, maybe everything is fake and I will never have an encounter with a pedestrian or a bus or something. So when they probably reach here, they are already informed about that, while when they are starting in each of the scenes, they don't know about this phenomenon and they perfectly respond to the design. So maybe segment 1 can best explain their behavior in each of the designs. And if we consider segment 1, painted bicycle path on the road and segregated bicycle path were found to be the least stressful environments, while sidewalk bicycling found to be the most stressful one. At the environment level, we did not find any significant difference in T-scores between different environments. However, at the segment-based level, we realized that the segment before intersection had been the most stressful segment as compared to the other segments, by having the segment 1 as the reference in the mixed model that is built here. Just to have a summary of the findings, we realized that the segregated bicycle path was perceived as the safest environment, and participants were most willing to bicycle on that under any condition, day, night, more than 10 minutes, less than 10 minutes with a child. Bicycling duration had a significant effect on willingness to bicycle of roadside and shared sidewalk. Participants considered cycling on these two environments for less than 10 minutes, but if they want to cycle for more than 10 minutes, their results significantly change, and they are not willing to cycle on these two environments anymore. No significant preference was found between painted sidewalk and painted road for less or more than 10 minutes. Segregated bicycle path and painted bicycle path on the road were found to be the fastest environments based on the data that was collected by the bicycle simulator. And if we consider section 1 as the bicycling environment, as a representative of the bicycling environment's stress level, sidewalk shared with pedestrians was most stressful. Bicyclists felt most stress right before the intersections, regardless of the type of the environment. So no matter what is the bicycle facility, intersections are just hard to deal with for the participants. As a conclusion, we realized that virtual reality is an exciting and promising tool for travel behavior research. And given the initial results, responses to virtual reality are comparable to reality and in agreement with previous research. There are obviously some limitations with this virtual reality method. Motion sickness and immersion duration. They were the two main factors that we couldn't have some turns, for instance, in the stretch of the road that we designed. The design was completely a straight line, because we realized that the turning movement in VR just creates a lot of motion sickness, and also the immersion duration. That 380 meters was just a suitable duration for them to cycle without getting some motion sickness effects. For choice modeling, it's a bit tricky virtual reality, because we cannot have two options right next to each other as we classically have in experimental designs to see the trade-offs between the two choices and select one of them. Each choice can be shown to the participants at once in virtual reality. So maybe in the future there are some technological improvements that lift these restrictions. And considering all of this, these virtual reality experiments are very time consuming. So each participant has to be surveyed one by one, and you can imagine for 100 participants how much time we needed. The future work, something that is remained from my study, is the comparison of these results to classic video-based surveys. We have also created the videos out of these 360 environments, and we have created the survey. If you are interested in this research and you have a panel of participants, please contact me to collaborate on a cross-border study to understand if there are any differences or similarities between the people preferences and perceptions with regards to cycling in these environments. Coming up, there will be a free webinar, The Global Cycling Momentum, on June 10, organized by PTV at 10 a.m. Berlin time. You can just go to the link that is written here and find out more about the panelists and the discussion. That was my presentation. Please stay in touch. And we can now go to the questions and answers. So if there are any questions, please feel free to write them down here, and I can assist you with any of them. Yes, there is one question, so let me just make it bigger to see the whole. Okay, the question is that how did you validate the model to the reality with regards to the stress level from the participants? This is a very good question. So we have quite a limited number of studies that have captured, or that they have actually studied the bicycling stress using the physiological sensors in reality. First of all, the validity of the results in reality is a bit critical because not everything is under control in reality. Different events happen to different participants while they are going through the same street or whatever during different time of the day. For instance, one participant might encounter a truck or something passing by, while the other participant might not encounter any trucks. So it's very hard to compare these results at the laboratory level to the real field observations. However, it's a valid point that these stress levels should be somehow validated to the reality measurements. There are some studies that have declared that most of the accidents, bicycle accidents, have happened at the intersections. So if we could correlate that to the stress level incurred by the cyclists at the intersections, then maybe we can somehow validate that, okay, there was a meaningful relationship between having a lot of stress right before the intersection and at the intersection, as compared to the accident levels and incident levels of the reality at the intersection. But for other road types, it's a bit hard just to validate all of these results to the reality. So yeah, that still needs to further investigate it. Thank you for your question. Yeah, we have another one. Okay. How the stress level is compared with types of vehicle? Again, this is a good question. So if I get this question correctly, it means that For instance, participants might have reacted to passing of the heavy vehicles or buses. However, they might not reacted to normal vehicles. This is something that I didn't look into, but this is a very valid point. So basically, we have the trajectory of all the agents from Vissim, and we have the trajectory of the participants riding in the design for every second. So if I match these two data sets, the trajectory of the vehicles and the trajectory of the participant, I can identify and then put the stress level on top of these. So 3 different data sources, which is a bit tricky. And identify, okay, if at that moment there was a bus, for instance, right next to the participant, and that was probably the source of the arousal or stress that happened to the participant, yes, it's doable, but the proper way to do it is just to control over everything, to have another experimental design in which, for instance, there is an empty scene, there is only one bus passing by, you collect the electrodermal activity of the participant, and then in the next scene, there is a normal car passing by, again, you measure this EDA arousal, and then you compare the arousal between the bus and the car while you are controlling for every other agents in the virtual reality. You can even add some eye tracking sensors to this setup to make sure that, for instance, the arousal was not due to observing some specific object in the scene based on the eye location of the participant, and also to have a more in-depth analysis regarding that. But to be fair, this experimental setup was not suitable for that type of analysis. This was also a very good question. Thank you for that. We have another one. Okay, we have a question. Did you consider the interference conflicts with other bicyclists in the study? If not, how will affect the other results? Okay, if not, if such an occasion happens, how will that affect the results? So again, one other limitation of this study is was that we couldn't create an interactive virtual reality scene. Meaning that if the bicyclist goes to the street and cycles there, the cars would pass through the bicyclist actually. So there will be an accident there. And we had also promised in the ethics approval not to have any accidents, by the way. So yeah, we couldn't actually create such conflicts with the proposed framework, and this is the framework for 2016, developed in that year. And I'm aware that PTV Vissim has created some new collaborations with other companies just to create this interface between Vissim and virtual reality 360 environment to enhance this interface. And probably in those environments, it works much better, and you can create such encounters between two bicyclists and vehicles and so on. I'm also keen to test those conflicts and those capabilities. The other thing is that there is this driver API in Vissim, which allows you to perfectly interact with other agents. We tested it for pedestrians, meaning that if you are moving in the scene as a pedestrian and not as a bicyclist, there is a surface, there is a walkable area, there are other pedestrians, you are walking towards them, and they perfectly react to you when you are approaching them. They just keep the distance based on the social force parameters that you have adjusted in your model. That API worked perfectly when you have two different agents as pedestrians on a walkable area. However, we couldn't get results for the interaction of bicyclists and pedestrians because, again, as I mentioned in the presentation, there is this interaction between the social force model and the car following model, which is basically used for the bicyclist, and this is not really well replicated, or at least at the moment it cannot be modeled easily in Vissim. So yes, this API can also work, but regarding the conflict, there is still much more to do, and I think with the technological improvements, this limitation will be also lifted. Okay. I don't see any other questions. That was the last question. Thank you very much for your attention to this presentation, and please stay in touch.